glass window, and which of these walls will lose more heat? The one with the glass window, because glass windows are thinner in sections, and also the conductivity of glass is higher than the conductivity of concrete walls. So the wall with the window is going to lose more heat. So bricks in one house and wood in the other house, and in this case we need to refer to the conductivity of these materials. The conductivity of brick is 0.72 watt per meter degree centigrade, and wood is 0.17 watt per meter degree Celsius. So almost 6 times smaller for wood compared to brick. The brick wall is given to be double that of the wood. So if the thickness is smaller, the heat loss should be higher, but the thermal conductivity of wood is 6 times smaller than the thermal conductivity of brick. Therefore, even if the thickness is smaller, the wood house will be far better in preserving heat. If the thermal conductivity, heat loss due to convection is low. Consider 2 walls of a house that are identical, except that one is made of 10 cm thick wood, while the other is made of 25 cm thick brick. Through which wall the house loses more heat in winter? If you substitute the thermal conductivities into this equation along with the thickness, the thermal conductivity of brick is equal to 0.72 watt per meter degree centigrade, and the thermal conductivity of wood is equal to 0.17 watt per meter degree Celsius. Then the length or the thickness of the brick is given as 0.25 meters, and the length of the wood wall is given as 0.10 meter. When we write Q in the wooden case, it is 0.17 times the area times T1 minus T2 divided by 0.10, which will give you 1.78 times T1 minus T2. And in the case of brick, this is equal to 0.72 times A times T1 minus T2 divided by 0.25. This is equal to 2.88 times A times T1 minus T2. Because the area T1, T2, all of them are the same in both cases, this is having a higher heat transfer. And so that is the one which is going to be the worst case. Wood is still performing better in this example. So without that data, it is difficult to come to these decisions, but that is what it is, okay? What is a black body? How do real bodies differ from black bodies? A black body is an ideal absorber and also emitter. So absorptivity and emittivity both are equal to 1 in the case of a black body, and other substances have less than 1 emissivity and absorptivity. Alright? And from here, all examples I solved. A wood slab with a thickness of 0.05 meters is subjected to heat flux of 40 watt per meter square. Remember, this expression, the 3 expressions that we have, should I write here? equations we have are Q dot is equal to Ka dt over dx. This is the total amount of heat transferred from one side to the other side. But if you consider this equation per unit area, it becomes Q dot over A equal to K dt over dx. And this quantity, heat transferred per unit area, is known as heat flux. We use small q dot to represent heat flux equal to K times dt over dx. In a similar way, we can write the heat flux due to convection, remove that area from there, and heat flux due to radiation, remove that area in the equation. So small q dot is per unit area, that is known as heat flux. So the data is given, length is 0.05 meter, q dot per unit area, watt per meter square, remember it's not watt. T1 is 40, T2 is 20. Use this equation, q dot equal to minus K, T2 minus T1. If you use the smaller temperature here, you put the negative sign, and that is minus minus, it gets cancelled, and the thermal conductivity is 0.10 watt per meter. It's a simple use of the same equation, but for heat flux. Is that okay? The inner and outer surfaces of a 4 meter times 7 meter, that is the area of a brick wall of thickness 30 centimeter and thermal conductivity 0.69 watt per meter Kelvin, or maintain the temperature 20 degrees and 5 degrees respectively. Determine the rate of heat transfer through the wall. Area is calculated. The length is the thickness here. 30 centimeters is 0.3 meters. And thermal conductivity is given. So T1 is given, T2 is given. Substitute in that. Remember, when you put the negative sign, you need to take the smaller temperature minus the larger temperature, so that this negative and that negative are cancelled, and you get, that is the rate of heat transfer to the wall. It's the same equation again. The inner and outer surfaces of a 0.5 centimeter thick 2 meter by 2 meter window glass in winter are 10 degree, 3 degree. If the thermal conductivity of the glass is 0.78 watt per meter Kelvin, determine the amount of heat loss through the glass over a period of 5 hours. What would your answer be if the glass were 1 centimeter thick? So, with the given data, Q dot is 4368 watt. I am just substituting the given data. And total heat transfer in 5 hours is, each hour is 60 times 60 seconds, and this is watt, joule per second. So if you are losing per second that many joules, in 5 hours it will lose times 60 times 60 times 5, which is equal to 786240000 joules. That is the total amount of heat lost in 5 hours, or 78,224 kilojoules. If L is 0.01 meter, 1 centimeter, you change the dimension there. It's 0.005, only you change that, you would have got 2184. The thickness is smaller. No, the thickness is bigger, so the heat loss is reduced. Can you see that? Because the thickness is in the denominator. Any question on this? An aluminum pan whose thermal conductivity is 237 watt per meter Kelvin has a flat bottom, that is there, 15 centimeter thickness, diameter 15 centimeter, and thickness 0.4 centimeter. Heat is transferred steadily to boiling water in the pan to its bottom at a rate of 800 watt. So we know Q dot. If the inner surface of the bottom of the pan is, that surface is maintained at 105 degrees Celsius, determine the temperature of the outer surface of the bottom of the pan. So okay, all of them are given, just use them and substitute in this equation. What is not known is what is the temperature on this side, T outer, and that is the one that I am calculating, 105.7641. There is only a slight difference because the thickness is so small. Alright? It's still the same equation. This is the same as the example that we have seen. To calculate the thermal conductivity, an experiment like this is done. In here, there is a resistance heater here. Heat is generated by connecting this to electrical power, and that power is equal to 25 watt. He gave you the power directly. 25 joules per second energy is drawn from the mains, and if we assume that all of that is going into these two solids, the two samples, and the rest of the data is T1 equal to 82 degrees, T2 equal to 74, and the area of the sample is given 0.01 meter square, and this heat that is centrally deposited between the two plates will be equally shared by both of them, and so the rate of heat transfer in each case is half of that, which is 25 over 2, and 12.5 is equal to minus Ka delta T over L. The temperature difference is 74 minus 82. I use negative and negative there, and solving the thermal conductivity of the sample is equal to 0.7813 watt per meter degree centigrade. So as you can see, it is all the same equation that is used again and again in different situations. Alright. Do you want to ask any question on this? Hollow sphere, a spherical iron container with outside diameter 20 centimeter and thickness 0.2 centimeter is filled with ice water at 0 degree, that is 0 degree, and the outside temperature of that surface is at 5 degree. Determine the approximate rate of heat gained by the ice water, that is, what is the amount of heat transferred from outside into the core, the ice water, is what he is asking, and determine heat gained by the ice water in kilowatt, and the rate at which ice melts in the container, because as the heat is added, ice will start melting, and he is asking at what rate it will melt. The heat of fusion of water is 333.7 kilojoules per kg. That means for each kg, that amount of heat energy is needed to convert ice into water. So the spherical shell area is pi times d square. That is the data given. Surface area of a sphere is pi times d square, and if you substitute that d, we can get the area of the surface, and q dot equal to minus Ka delta T over T, and that delta T is 0 to 5 degrees, or 5 degrees to 0 degree, because I use negative here, I use negative there, and q dot is so many watt. Now out of this energy, for each kilogram of ice to melt, that much joules is necessary, and so if you divide this with that joules, it will be the rate at which ice melts is that total heat, the rate of heat transfer divided by this amount of heat required per unit kilogram, per kilogram of ice to melt, and so from there you get 0.0755 kilogram per second. That is the, for each second, that is the amount of ice that is going to be melted. To check this, you see, that is what? This is heat of fusion joule per kg. So watt is nothing but joule per second times this kg goes up and joules comes down. This is kilogram per second. So that's how the rate of heat transfer into the center is able to convert so many kilograms of ice per second into water. And this one, in a power plant, pipes transporting superheated vapor is going through it at the rate of 0.3 kilogram, flowing at a rate of 0.3 kilogram per second inside a pipe 5 centimeter in diameter and 10 meter long. The pipe is located in a power plant at 20 degrees surrounding temperature and has a uniform surface temperature of 100 degrees. Surface temperature is 100 degrees. If the temperature drop between the inlet and exit of the pipe is 30 degrees Celsius from here to there, and the specific heat of the vapor is 2190 joule per kilogram Kelvin, determine the heat transfer coefficient as a result of convection between the pipe surface and the surroundings. All this data is given to calculate what is the amount of heat loss from the vapor to the surrounding, and that is Q loss is equal to mCp delta T. Anytime we have come across with this equation in thermodynamics as well. If I give this problem, I'll give this equation. I don't expect you to remember equations. This is not there in our formula sheet. If I give this problem, I will give this equation. The heat transferred when you are converting, when you are transferring heat into a body is equal to mass times Cp times delta T. And if you take the mass flow rate, this will become the heat flow rate into the body or outside of that. So for this superheated vapor that is going through it, as the temperature is falling through 30 degrees, delta T is 30 degrees, and its mass flow rate is 0.3 kilogram per second, and its specific heat is 2190, and that much of heat is flowing out of the steam into the surroundings, and that is Q dot. Once you have Q dot, that amount of heat energy is lost from the pipe surface to the surroundings, and the surface area of the pipe surface is that lateral surface area, which is pi times the circular length pi d times L. So pi d times L is the area, and Q loss per unit time is equal to the Q due to convective heat loss equal to H times AS T surface minus TA. So substitute the known quantities from that. This H value is the convection heat transfer coefficient 156.8468 watt per meter square degree Celsius. Now the only difference here is it's just Q dot equal to H times A times temperature difference. That is the same equation, but that additional calculation is given to know what is the amount of heat transfer from the superheated vapor to the surroundings, and that one additional complication is coming. Otherwise, it is the same equation. It looks complex, but it's very simple problem again. A transistor with a height of 0.4 centimeters and the diameter 0.6 centimeter, so we can calculate the surface area through which heat is being lost. That bottom, which is in contact with this one, is not losing any heat. So only that lateral surface, the cylinder, plus the surface of the circle on this side are the areas through which heat is lost from the transistor to the surroundings. Can you please keep quiet, sir? Please. And H, the heat transfer coefficient is given. The surface is at 70 degree and the surrounding A is at 50 degrees Celsius, and Q dot is HA, is surface minus TA, and we are substituting all that. The area is the area of the circle, which is pi r square, plus the area of the cylinder, which is pi d times the length. I just calculated that, or 2 pi r times length. And Q dot is 0.0467 watt. That is the rate at which heat is being lost from the transistor to the surroundings. Another problem where electric heating is used to heat up that wire, and the voltage is 110 volt, current is 3 ampere, therefore the rate of heat consumption is VI, which is 330 watt, and heat is lost on the lateral surface of the wire. The surface of the wire is pi times d times the length, and that is the surface area, and Q dot electrical is equal to Q dot convection, because we are assuming steady state. Whatever is generated is being continuously lost. So that is equal to H times AS to surface minus TA. Substitute that and we get H from this as 170.4545 watt per meter square degree Celsius. That is convective heat loss. We are getting into radiation now. The outer surface of a spacecraft in space has an emissivity 0.8. This is emissivity. And a solar absorptivity of 0.3. That means the energy from the sun is absorbed at the rate of 0.3 and it can emit at 0.8. If solar radiation is incident on the spacecraft at a rate of, that is the radiation due to the sun energy falling on that, determine the surface temperature of the spacecraft when the radiation emitted equals the solar energy absorbed. Emissivity is given, absorptivity is given, Q dot solar is given, the surface temperature is what, and the space is considered to be at absolute zero, which is minus 273 degrees Celsius or 0 Kelvin, that is 0 K. So radiation absorbed is equal to radiation emitted, but radiation Q dot absorbed is Q dot emitted, but Q absorbed is absorptivity alpha times the energy that is falling, which is Q dot solar, equal to the Q dot emitted is epsilon sigma AS T surface to the power 4 minus T surrounding space to the power 4. This is Stefan Boltzmann's equation. Substitute all the known quantities here. The area of the surface is not given, but it is equal on both sides. You don't need to worry about it. From this, the surface temperature is 281.5418 Kelvin. Alright. Can you please keep quiet, sir? There, please. That is the surface temperature. This problem is very similar to the example problem we solved for the girl standing in the room, the amount of heat radiated, and so I will leave it with you to ponder over. And this is again very similar. Area is given, the radiation, radiative heat loss is given, and that is equal to this. So from that, the surrounding temperature is calculated. Keep quiet and don't leave. I have still 10 minutes time before I complete. 2 o'clock. Okay. And when two mechanisms are simultaneously happening, like for example in this case, heat is being transferred from inside through conduction into the wall, and some heat is lost due to convection. So there is convection, there is convection, and for a steady state, the rate of heat transfer due to conduction must be equal to the rate of heat transfer due to convection. And so from the given data, per unit area, you can use the heat flux, which is the same equations without areas. K T1 minus T2 over L equal to H times T2 minus T infinity, where T1 is the temperature of this side, T2 is the temperature of this side, T infinity is the surrounding temperature. Substitute all the known values and solve for the unknown quantity, which is the temperature T2, the temperature on this surface. to calculate what is the amount of heat transfer, because the heat transfer due to conduction is equal to the heat transfer due to convection. Either you can use this equation, Q dot heat flux due to conduction is K T1 minus T2 over L, or H times T2 minus T infinity, one of those equations, and you will get the same answer whichever equation you use, once you know the temperature. In this case, a solid plate with a thickness of 15 centimeters, that is the thickness, and a thermal conductivity of 80 watt per meter Kelvin is being cooled at the upper surface by air. So this is hot inside and it is losing heat to that. And heat is transferred from this surface to this surface due to conduction, and then due to convection heat is lost into the surrounding. Determine the convection heat transfer coefficient. What is the convection heat transfer coefficient here? That's the problem. So again, here all the dimensions, whatever is given is written, and then when steady state is maintained, the conduction rate of heat transfer due to convection is equal to rate of heat transfer due to convection, because here there is no reference to the surface areas. I am using the heat flux, which is per unit area, that is K times T S2 minus T S1 divided by L equal to H times T surface minus T infinity. So from this we can calculate what is the convective heat loss coefficient. It is coming out to be 133.3333 watt per meter square Kelvin. He is asking to comment whether it is really good or bad. It is really good because on an average, if you keep a body in still air, the convective heat loss coefficient is expected to be at around 5 to 8 watt per meter square degree centigrade, which is 5 to 8, and this is 133. That is happening because of the forced air here. In still air, theoretical lead is calculated, that is 5, but here we are getting 133 because of the forced air that is taking a lot of heat. And this problem is very similar to the other problems, but here that iron at at a higher temperature is losing heat. The heat energy in the iron is 1000 watt, and that is losing heat to the surrounding as well as the walls of the room. So there are two mechanisms suggested here. One is convective heat loss with a coefficient 35 watt per meter square Kelvin, and radiation heat loss with an emissivity epsilon equal to 0.60, and the surface area of the iron is 0.02 meter square. Now this is a combined heat loss considering both convection and radiation. The total heat loss is equal to the heat it is drawing from the electrical supply. Q dot electrical equal to Q dot convection plus Q dot radiation. The convection is the surface H times AS times the surface temperature of the iron minus surface temperature of the air, and due to radiation epsilon sigma AS Ts to the power 4 minus Ta to the power 4. This must be equal to the electrical energy it is drawing from the mains, which is given as 1000. Substitute all these quantities, simplify this, you will end up with that equation, and I need to solve that equation. And we came across with a similar such situation in statics also earlier, or no, in dynamics also earlier. I told you when you face very difficult equations like this, the best way is to go by trial and error method. That is, I just started with assuming Ts as 1000, I am getting 1380, but that is bigger than that. So So I reduced to 900, it is coming out to be smaller than that. So it is between 900 and 1000. Then my guess was 950. I'm getting 1218, very close, but still higher. So I reduced by 5 degrees, 945. It is 1203, smaller than 1210. So somewhere in between, I assume 947 and substitute. I'm getting 1209.80, which is very close to 1210, and that is my final solution. So the temperature on the surface is 947 degrees. This is Kelvin, so the surface temperature is minus 273, 674 Celsius. 2 minutes time is there, don't worry. Alright, these last few couple of things, I will quickly cover these, discuss these in the additional tutorial tomorrow. In the meanwhile, I will upload these solutions online. Can you please go through them, and if you have any problem with any of these, please raise them in the class tomorrow. Okay? I will quickly go through the remaining few problems in this week tomorrow in the additional tutorial session, and then immediately solve all the problems in the model exam. Please focus on the model exam.